So here's our example. I'm going to take this object, this medicine ball, an initial height of 2.0 meters, and I'm going to drop it. And we're going to analyze what happens during that situation. So I'm going to take the medicine ball. I'm going to drop it from a height of 2.0 meters. And I want to know what is the velocity right before so here's the medicine ball. Starts out at an initial height of 2.0 meters above the ground. It's going to fall, hit the ground, and I want to know what is the velocity right at that point, right before it strikes the ground. You'll notice one thing that I'm not writing down is the mass of the medicine ball. That's because the mass is irrelevant. Irrelevant. So the mass is irrelevant. The acceleration in the y direction is equal to negative 9.8 meters per second squared, and that is irrelevant of the mass of the object. And I'll take an opportunity to prove that a little bit later. We can't quite prove that today, and we'll do some exercises talking about why the mass is irrelevant. But I can't quite do it yet today. So, dropping the ball from a height of 2.0 meters, what is the velocity right before the hitting the ground of the medicine ball? Parth, please list for me givens that we know.
The initial height is 2.0 meters.
Right, but I already have the initial height over there. Part of the thing here is we need to translate. So what is that? What kind of variable is that going to be for us?
Displacement.
So the displacement. Now, normally I would put delta x for displacement, but because everything's in the y direction, we're going to use y's for this. So the displacement in the y direction is equal to 2.0 meters. Keep going, Parth.
The final velocity is 0.
The final velocity in the y direction equals 0. Okay. We're going to talk about why that's wrong. Okay. It's a common thing to say, because if you look at the medicine ball right now, what's its velocity, class? 0, right? Absolutely. I do agree that the final velocity of the medicine ball is 0. It's stopped. Why can I not say that according to what we've got here? Jacob.
You're not including it in the problem. You're trying to find the velocity before it hits the ground.
Before it hits the ground, what happens when it hits the ground?
The force of the floor.
There's a force and all that stuff. We're not hitting the ground yet. We're no longer in free fall. We're concerned with the free fall portion. So Parth, you're absolutely correct. After it strikes the ground, that final velocity does end up being 0, but we're talking about free fall while it's not touching any other object. So as soon as it touches the ground, it's no longer in free fall, not a part of the problem anymore. Okay? This final velocity in the y direction, ooh, new eraser. Let's see how that works. Is what we're looking for. This is the final velocity in the y direction, right before it strikes. What else do we know? Alex? So, we need one more.
Is the initial velocity 0?
How do you know the initial velocity in the y direction is equal to 0? I drop the ball. So I'm simply holding the ball and I let go of it so that initial velocity is equal to 0. You can see we have our 3 UM variables and we can simply find the other one here. Yes, Nate?
Doesn't acceleration just equal positive mass coordinate?
Remember, it's an object in free fall, so the acceleration in the y direction equals a negative g, which is negative 9.8 meters per second squared. So we have what we need. All we need now is the correct equation. Please, Megan, give me the correct equation.
I know it's going to be like a
This is true. There are 4 to choose from.
VF
VF.
velocity final equals velocity initial plus accelerate, or wait, that won't work. Hold on.
That's fine. Let's finish.
Well,
That's it. Acceleration times change in time. So Shia, why won't this work?
because there's no time.
We don't know the change in time. That's fine. Keep going.
Okay. Here's at like a 2-second moment for velocity, yeah, both those count. And then plus 2 times acceleration times the change in position.
Right. Now, because we're in the y direction, I'm going to put y's for this. Velocity final in the y direction, velocity initial in the y direction, the acceleration in the y direction. And rather than delta x, we're going to have delta y. Now, I do understand that everything here is in the y direction. And when we started doing this, we didn't identify that everything was in the x direction. But pretty soon, we're going to move on and have things moving in both the x and the y direction. So the reason we're adding the y's today is to get you used to identifying the direction, because eventually you will have both an initial velocity in the x direction and initial velocity in the y direction, a displacement in the x direction, displacement in the y direction. And all those variables will need to be identified as either x or y. So we're starting by just identifying everything with our y's here. So we have the initial velocity in the y direction, which is 0, which we're going to square, plus 2 times the acceleration in the y direction, negative 9.8, multiplied by the displacement in the y direction, which is 2. So the velocity final in the y direction squared is equal to all of those numbers. So the final velocity in the y direction, taking the square root of both sides, is equal to the square root of 2 times negative 9.8 times 2. This is where you should have out the calculator. You should be doing your calculator calisthenics, making sure the calculator knows what it's doing and is warmed up and ready. Because when you go through and you use your calculator, you discover problems, don't you, Park?
Yeah.
What do you find?
Can't take the square root of a negative number.
Your calculator's not happy with you at the moment because you're trying to take the square root of a negative number. Anytime you try to take the square root of the negative number in this class, you've done something wrong. So we've done something wrong. I need to know what it is. Out.
So it's on y, or the change, or the displacement, is it negative?
Y is the displacement in the y direction equal to negative 2.0 meters. Yes, why?
Because you're headed in the downward direction.
Remember, displacement has both magnitude and direction. The direction is down, and we have defined the down direction as negative. There are two ways to look at it. We know displacement is equal to y final minus y initial. The final height is 0, the initial height was 2, therefore we get negative 2.0 meters. You can also simply say that the displacement in the y direction is equal to negative 2.0 meters because it's moving down. Either way is fine, but I'm just showing you specifically that you can see the displacement in the y direction is 0 minus 2. Great. So when we have a negative 2 for our displacement, we are actually taking the square root of a positive number because a negative times a negative is a positive. That's good. That's plenty, thank you. So 6.3 meters per second is our final velocity in the y direction. This is velocity right before it strikes the ground. Great. Now, part B, I want to know how long did it take? The change in time equals question mark. Brad?
Wasn't the answer supposed to be in C?
Actually, no, because the 2.0 only had 2.
Oh.
Yes, 9.8 has 3, but because we have the least number of sig figs at 2.0, we should have that. So, Chi,
Do you know the direction from the point?
we do. All right. Sure, we'll do that. Okay, change in time we're trying to find. Okay, how are we going to do this, Rosa?
Use the equation G, velocity final, equal to velocity initial plus
what is missing from this equation, Mohammed?
The y subscript.
All the y's, right? Because remember, this is the final velocity in the y direction, the initial velocity in the y direction, the acceleration in the y direction. Right? So just make sure to add all those y's. Final velocity in the y direction, 6.26099 is equal to the initial velocity, 0, plus the acceleration in the y direction, which is negative 9.8, multiplied by the change in time, which is delta t. Delta t, the change in time, equals 6.26099 divided by negative 9.8. The change in time is equal to. What do we get? Change time. Please. Out.
-.638876.
That's plenty, thank you. That's good. So negative 0.64 seconds. Negative time. Does that sound good? No. Every once in a while in AP we do talk about negative time, not in this class. Anytime you get a negative time in this class, you've done something wrong. What did we do wrong? We're very close. Very close, Mom.
The velocity is down, should be negative.
The velocity is down, therefore it should be negative. We should have given our answer as a negative 6.3 meters per second. Now, how does that work? How do we get a negative out of this mathematically? No. We need all sorts of bus drivers. Everybody's got to drive the bus. You know this. Everybody's got to take a turn driving the bus. Dimitri, you got to drive the bus too? Josh, there's a bus. We're all driving it. We can't all just be passengers on the bus. Mathematically, who could tell me how it is that we can get a negative out of this part?
When you take a square root of a number, you can get a positive or
You all are a technology generation. You love your technology and you believe whatever it says. But I'm here to tell you right now that whenever you take the square root of a number, your calculator lies to you. It only gives you one of two possible answers. Whenever you take the square root of a number on your calculator, you need to be smarter than your calculator and you need to think, is it positive or is it negative? We know this answer is negative because it's going down. Therefore, our answer is negative 6.3 meters per second. Therefore, we need to use a negative on our final velocity in the y direction. Therefore, we end up getting a positive time. So please be smarter than your calculator.